So today we will discuss some solved examples relating to landfills, mostly relating to liners and covers. And the idea is that by doing about 10 examples, you will get to know what kind of leakages occur. And we discussed action leakage rate, that if the leakage is more than a particular value, then we have to take some action. So from where does that value come? What is the logic behind it? That will also become apparent as we discuss these examples. So the first example is advective flow through a compacted clay liner. As I talked to you in the very beginning, that flow through liners can be advective or diffusive. Advective is due to hydraulic gradient and diffusive is due to gradient in concentration. And we know that for advective flow, the Darcy's law is valid. So now what we are going to see is that if 0.3 meter of leachate is ponded on a compacted clay, I'm not talking of a composite liner, just a compacted clay liner, which meets our specifications of 1 into 10 to the power minus 7 centimeters per second, then what is the flow rate which occurs under steady state condition in liters per hectare per day? Liters, because you understand what a liter is. You have seen a 2 liter bottle, the one in which you get your big Coke or Pepsi. So when I say 20 liters, you are able to understand it is 10 such 2 liter bottles. Per hectare, a hectare is 10 to the power of 4 square meters, that is 100 meters into 100 meters, almost like a football field or a cricket field per day. So how many buckets or how many bottles of water come out per day? So this is what has to be calculated as per the Darcy's law. What this question is saying is that you have your clay, and you have the drainage layer, and leachate collection layer at the top, and there is some leachate in that. So this is 0.3 meters and the compacted clay is 0.9 meters. And we want to know if this situation occurs, how much water will come out in a football field per day. And then if, for example, the question says, if by chance we wanted to have a permeability of 10 to the power of minus 7, but the compaction was not good or the quality of soil was not good enough, and by mistake you get 10 to the power of minus 6 instead, what happens to this leakage rate? And finally, we would like to compare it with the action leakage rate and the rapid large leakage rate which the US EPA has stated. So please use these formulae. You remember Q is equal to KSIA, hydraulic conductivity, hydraulic gradient, and the area, right? And what's the hydraulic gradient in this case? H plus D over D, where H is the leachate head over the liner. In this case, it is 0.3 meters, and the thickness of the liner is 0.9 meters. So can you please calculate Q for me? As per this formula, it will come out in centimeter cube per second, but I want you to compute it in liters per hectare per day. Please note these two formulae, and then I'll go back to the problem. And here is the problem back again. If you have noted the formula, 0.3 meter is the head, 0.9 meters is the thickness of the compacted layer, and the conductivity is 10 to the power of minus 7 centimeters per second. So if you put in these values, what is the value of I that you get? I is equal to and with that you can do Q is equal to and all you have to do is convert it to liters. So 1000 cc equal to 1 liter, if you recall, and 10 to the power of 4 square meters is 1 hectare. So can you give me a value which you get in liters per hectare per day? So K is 10 to the power of minus 7 centimeters per second, which becomes 10 to the power of minus 9 meters per second into 1.33. So this becomes so many meter cubed per meter square per second. And this whole thing, if you want to convert it into a hectare, you have to multiply 10 to the power of 4. And if you want to convert it into a day, 60 seconds, 60 minutes, 24 hours. Is anybody able to give me a value here? What is the value that you get in liters per hectare per day? Anybody has taken out a value? So my calculation is 1152, but you'll have to confirm it. Has anybody got 1152? Okay, great. So what we have to see is that if I have a good, well compacted clay liner, I'll get 1,000 liters per hectare per day. Okay? And if a bucket is 20 liters, how many buckets is that? 1,000 liters? 50 buckets per day. So if you compare it now with the action leachate rate which we had talked about, that it is 935. 935 is the same as 1,000. So the 1,000 comes from this. That means if it exceeds 1,000, you have something to worry about. The next question is, if by mistake or by construction practices which are not very good, you have not done good compaction, you started with a soil which had significant plasticity, but from the borrow area the soil which is coming now does not have that much plasticity, then maybe the K can become 10 to the power of minus 6 centimeters per second. That is above. If this becomes 10 to the power of minus 6, what happens to Q? Q becomes 11520. That means it has become 10 times what is acceptable. And large leakage rate, if you recall, that was 9350. So this 10 times means that you are having a liner which is not even performing like a 0.9 meter thick compacted clay liner. So that is the basis of fixing up the action leachate rate. And if you have large leakage, then what happens? You have to shut down. You have to take action to reduce the leakage. Otherwise, you have to plug the liner system. Okay, let's say that we were using a geomembrane alone. Okay, so the second example that we are going to do is advective flow through geomembrane. Now, do remember that I do not have a precise hydraulic conductivity value for geomembrane. I have some presumptive values because I use some water vapor transmission test, and on the basis of the water vapor transmission test, I can get an equivalent hydraulic conductivity for ease in calculation. And just like we said that the clay has a hydraulic conductivity of 10 to the power of minus 7, let us say the presumptive hydraulic conductivity of geomembrane is 10 to the power of minus 13. Can you now tell me what is the Q coming through the geomembrane? Same formula, but now the thickness instead of being 90 centimeters has become 1.5 millimeter. So if I just take a 1.5 millimeter geomembrane and put some water on it, which has a leachate head of 0.3 meters, and an equivalent presumptive hydraulic conductivity of 10 to the power of minus 13, what kind of Q will come out? We know that for clay it's about 1,000 liters per hectares per day. Can you please compute the Q which will come out through a geomembrane with no puncture? Same formula, except you substitute K with 10 to the power of minus 13 centimeters per second, and the hydraulic gradient will change. In fact, can you tell me what is the hydraulic gradient here? 201. And what was the hydraulic gradient in the clay? 1.33. So the hydraulic gradient is very high. So consequently, what do you get as your Q in liters per hectares per day. So with the hydraulic, anybody would like to give me a value? 0.17. So you should get 0.17, which is also what is found from water vapor transmission. Here there is an error because 100 has not been applied to the 10 to the power of minus 13. But anyways, the solution that we get is 0.174 hectares per day, liters per hectare per day. So right from 1000 to 0.1, that's what is the effect of a geomembrane. But let's make a hole in this geomembrane. Let's make a puncture. If I make a puncture, what happens? Water will flow through an orifice. And let's assume I have a circular hole and we have to give the area of the hole, but then I have the Bernoulli's equation for flow through an orifice. Okay? So the same example I would now like you to take at 2 punctures per hectare, and the circular hole of area 100 millimeter square. That means 1 centimeter square in 1 hectare. So if I have 2 holes, which is very good quality construction, if you will go recall, in 1 football field, for you to get 2 holes which have 1 centimeter square in area is very, very good, excellent quality of construction. The formula that has to be used is the formula for flow through a circular orifice. And please have a look at this formula and note it down. Q is equal to CB into A, where CB is the flow coefficient and we take it 0.6 for a circular hole. A is the area of the circular hole in centimeter square. 2GH. G is the acceleration due to gravity and H is the liquid head above the liner. So same problem. We are now looking at, if I make 2 holes, what is Q? Please do this computation for me. And in this formula you can use CB equal to 0.6 and you'll have to multiply this with 2 because this is per hole. Okay? You'll have to multiply this with 2 because this is per hole. G is 981 and H will be 30. For compacted clay liner we had got 1152. What do you get for geomembrane with 2 holes? 0.29. That's very low. I can immediately feel that if it's a hole of 1 centimeter square, water is going to come out very fast. I'm going to fill several buckets. Let me see what the calculations reveal here. Anybody has got this value? So it's about 25,000. So a huge jump. A geomembrane is virtually impermeable, very little water comes out of it. But if you make a hole or 2 in it, everything flows out. Anybody who is not reconciled to this value? And I have to remember action leakage rate was 935. So let's see, do we have any evaluation methodology for a composite liner? So this is from the Darcy's law. Darcy's law, flow through an orifice. For a composite liner, we have some empirical results, some empirical formulae which have been given to us. So if I use the same geomembrane and the same compacted clay, 1.5 mm thick geomembrane, 0.9 meter thick clay, again 2 punctures in 1 hectare, then I have some empirical formulae for good contact and for poor contact if the hydraulic gradient is 1. These were studies which have been done by Giraud and Bonaparte and Giraud. So these are empirical, these equations are not dimensionally consistent. So you have to use the values which are given here. Okay? Same problem as before. If I have good contact, it becomes 0.21 a to the power of 0.1, h to the power of 0.9, k h to the power of 0.74. So if you use the area in meters square, if you use the head in meters, and if you use Ks in meters per second, then you will get the Q in meters cube per second, right? So per hectare we have to compute what is the quantity of leachate. So please note the first formula, substitute the values, and this is for one hole, and if there are 2 holes in a hectare, so you'll have to multiply it by 2. And what is good contact and what is bad contact? Good contact means few wrinkles and poor contact means large number of wrinkles. So in a way, when they did the testing in the laboratory, this was the compacted clay. A good contact meant this, and a poor contact meant. So what was done was, the wetting front in a poor contact was much wider than a wetting front in a good contact. So consequently, you would get larger leakage. So please apply the formulae, take it as an empirical formula and give me the values for So the computations shown here give you 1.08 liters per hectare per day for good contact and 5.91 liters per hectare for poor contact. Please confirm this. Anybody has got these values? Q into 0.21 into a to the power of 0.1, 0.3 to the power of 0.9, 10 to the power minus 9 to the power of 0.7 into 2. You will have to use the function a to the power of b in your calculator, or you have to do log. Is anybody confirming this value? You also? Good. So for good contact, I am getting 1.08, and this is about 5 times. So what do these examples show us? The examples show us that our action leakage rate is about 1000 liters per hectare per day, which is what we would get with a compacted clay liner, which is relatively thick and has a head almost equal to the thickness of the leachate collection layer on top. If I use a geomembrane alone, it looks very good, but no geomembrane can be laid without a puncture, so a geomembrane with puncture is bad. However, if you put both of them together, even if there is puncture in the geomembrane, the leakage is very, very small. So that is why we use composite geomembrane plus compacted clay liners at the base of a landfill. Any questions? Okay. If there are no questions, then we would like to go to the issue about comparing compacted clay liners with geosynthetic clay liners. Okay? You recall that we had said that if you can get low permeability thin material, then it can also perform as well as a compacted clay liner. So I am going to compare 4 aspects of this comparison. Advective mass flux is the same as advective flow. So if I have a compacted clay liner which is 90 centimeter thick, has K 10 to the power of minus 7 centimeters per second, the head is 30 centimeters, and I compare it with a geosynthetic clay liner of thickness 7 millimeters. So a 90 centimeter thick clay has been replaced by 7 millimeters, and because it has got sodium bentonite in it, its permeability is 1/100th of the compacted clay. So what are we comparing? We are comparing same leachate head, but now that is your seven millimeters. It's thicker than a geomembrane. It's thicker than a geomembrane, which is 1.5 mm. But the GCL is supposed to be self-healing. So if you have a puncture, the bentonite will expand and heal itself. So we are going to now compare the Q through both of them, right? But this problem is presented. So please understand, once again, your hydraulic gradient is going to be very high here. Just like you're at 201, you're going to have a high hydraulic gradient here. But the permeability of this is much lower. And we'll do this comparison in terms of the advective mass flux. We are saying that this leachate has 600 milligram per liter of chlorides, of chloride ions. So we want to know how much chlorides will come out of the compacted clay liner and how much chlorides will come out of the GCL, and compare the two. So when you are doing advective mass flux, then the equation that you use is similar, except that you multiply the concentration with V. So the average seepage velocity of flow through the liner is Q by A, which is Ki. Okay? So the advective mass flux in milligram per centimeter square area per second is Ja is C naught into V, please note this down, which becomes C naught into Ki, and which becomes C naught into the H plus L over L. So just note down this formula. And please be consistent with your units: milligram per centimeter square per second, milligram per centimeter cube. In our case, I have given you the value which is normally we use in the Indian standards in terms of milligram per liter, because that works out like parts per million. So using these concentrations, you can compute the Ja both in the compacted clay liner and in the GCL. So compute the advective mass flux using this formula. You have C naught, 600 milligram per liter. You have K, if it is compacted clay liner, it is 10 to the power of minus 7 centimeters per second. If it is GCL, it's 10 to the power of minus 9. H plus L vary. H is 0.3 meters in both the cases, but L is varying. Okay? So what is the advective mass flux for the first case in the compacted clay liner, and then the second case in the GCL? In the GCL, please note 10 to the power of minus 9 centimeters per second is the K, This was 600 milligram per liter. So we are trying to convert milligram per centimeter cubed. So 600 by 1000. Head is 30 centimeters. Thickness is 0.7 centimeters. And you should get this value of advective flux through GCL. Please confirm that you are getting this value. Anybody is confirming it? Okay, great. Then if you go to the compacted clay liner, the concentration is still the same. Two things happen. Permeability is 10 to the power of minus 7 and the hydraulic gradient changes. And this causes the advective mass flux to be 80 into 10 to the power of minus 9 milligram per centimeters per second. So what does this show us? Which is transmitting more? Compacted clay liner is transmitting more. So GCL is better because we want less mass flux. We want less chlorides to flow out. So this shows that the ratio of GCL to CCL is 0.33, which is less than 1. Therefore, the geosynthetic clay liner passes less advective flux than CCL. But the other thing which I would like to study is how quickly does it come out? How quickly does it come out? So suppose we have two liners. If I have a geomembrane, the moment it is punctured, how quickly does the leachate come out? Instantaneously. But if I have clay, it takes some time for it to travel through the soil. So it takes maybe a few months, maybe a year or so. So that's the next aspect we are going to compare. We would like to compare the advective breakthrough time. That means in how much time does the leachate come below the liner? That means, you see, as far as your design is concerned, this is an impervious layer. One is thin, one is thick, one is low permeability, one is a little slightly higher than the low permeability of the GCL. Now, what we are saying is, compare the advective breakthrough time for CCL and GCL in the previous example. The additional data that is given to you is that the porosity for compacted clay liner is 0.5 and the porosity for the geosynthetic clay liner is 0.6. Okay. That's the additional data. We are still continuing with the same example. And the way to tackle this is as follows. We know that V is equal to Ki. And V is called the average seepage velocity of the flow through the soil or through the liner. We first compute not the average seepage velocity, but the seepage velocity through the voids of the liner. So Vs is defined as the seepage velocity through the voids, which is nothing but V divided by porosity. So I can get the value of Vs. If I know the value of Vs, the leachate has to travel the length L, which is the thickness of the liner. So the breakout time is L by Vs. So in both your problems, first find out Vs. You can compute it in centimeters per second, or you can compute it in meters per second and then convert it into meters per year. You will get an idea as to how quickly it is traveling. How many meters per year is it traveling? Okay. So with this we can find out the breakthrough time. So let us first look at CCL in 10 to the power of minus 7 centimeters per second, 30 plus 90 over 90 into 0.5. This is the porosity effect. And the seepage velocity will work out to be 8.4 centimeters per year. So the important thing which I am trying to tell you is Q is large. How much is the Q? 1151 liters per hectare per year. The question is, when does it start to come out? And if you look at this, our Vs in the compacted clay liner is 8.4 centimeters per year. And how many centimeters does it have to travel to come out of the liner? 90. So 90 divided by 8.4, 10.7 years is the amount of time when your leachate will come through. So you won't see any leachate at the bottom of the compacted clay liner till 11 years have passed. That's a huge amount of time. Just if you had a much lower permeability of the soil, let us say 5 into 10 to the power minus 8, then it would have been even longer. Let's look at the seepage velocity in the geosynthetic clay liner. Well, here we are. This is a lower permeability value, but the hydraulic gradient is higher, and you get 2.3 centimeters per year. So the seepage velocity through the geosynthetic clay liner is lower. However, the thickness of the geosynthetic clay liner is lower. So the breakout time in the geosynthetic clay liner is 0.7 centimeters divided by 2.3, 110 days. That's about 3 to 4 months. So the leachate will come out of the geosynthetic clay liner much faster than it will come out of the compacted clay liner. So once it starts to come out, the mass flux is going to be higher in the compacted clay liner. But till it comes out, it is all inside the clay. Till it comes out, it is all inside the clay. So in that sense, because the breakthrough time is much shorter in the GCL, the performance of CCL is better as far as breakthrough time is concerned. And this you have to realize, that the performance, when you are trying to do equivalence, you are not only trying to do equivalence in mass flux, but you are also trying to do the equivalence in when it comes out at the bottom. So the breakthrough time is much longer in compacted clay liner. Anybody is confirming these values for me? Just so that I have not made an error in computation. Okay. Can we move forward? Anybody has a doubt? We have so far focused on advective mass flux. That means due to difference in head. We can also look at diffusive mass flux. The diffusive mass flux requires us to use the Fick's law. And we have not gone into detail about the Fick's law in our classes, but I'll give you two formulae which we are going to use here. And we are going to use a parameter called the effective diffusion coefficient. So for the same problem, we are still comparing the CCL with the GCL. We want to find the diffusive mass flux through the CCL and the GCL, given that the effective diffusion coefficient D dash for the non-reactive chloride solute, if it was reactive, it would be attenuated, and therefore it would be a different value altogether. So for the CCL, it is 6 into 10 to the power of minus 10 meters square per second, and for GCL, it is 2 into 10 to the power of minus 10 meters square. Please note, permeabilities can vary by 100 times or 1,000 times. 10 to the power of minus 7, 10 to the power of minus 9, 10 to the power of minus 13, right? But diffusion coefficients within the soil will vary not more than an order of magnitude of 2, 4, 6, 8. So here it is 6 and here it is 2. Now assume steady state diffusion conditions. So this is an idealized problem. Steady state diffusion condition means there is a C at the top and there is a C at the bottom and it remains fixed. Transient means that as it comes through, C at the bottom will start to rise. If I have a concentration of 600 milligram per liter at the top and 0 milligram per liter at the bottom, if I am saying that this is a steady state condition, which means I am flushing the bottom all the time, and this remains at 600 and this remains at 0. But as it starts to come through, this 0 will begin to rise, and that is transient case. So we'll look at the transient case a little later. At the moment, we are assuming steady state diffusion conditions only. And the formula that we use is called the Fick's law of diffusion. We have done JA earlier. JD is equal to the effective diffusion coefficient D dash into the porosity, and that is the concentration gradient. Please have a look. So here we are saying 600 milligram per liter at the top, 0 milligram per liter at the bottom. Please tell me what is the diffusive mass flux. Please tell me what is the diffusive mass flux. So you have been given D dash, you know delta C, 600 minus 0, you have the liner thickness. So having these components, you can find out the JD. Do remember that the diffusion coefficient will depend on the contaminant that you are tracking. We are saying this is the coefficient for chlorides, which is a faster one which travels because it is non-reactive. It will depend on also the type of soil, the tortuosity of the pores. That is why you find that the diffusion coefficient for a GCl is lower, because the tortuosity of the pores is larger. So in one case it is 6 into 10 to the power of minus 10, in the other case it is 2 into 10 to the power of minus 10. So just apply this and give me the values of the diffusive flux and compare the two. So can somebody confirm for me this value? You've got it independently? Great. So this is 2 into 10 to the power of minus 8, and GCl is 102 into 10 to the power of minus 8. Why did that happen? Because the gradient is over here, this drops over 90 centimeters, concentration gradient. Here the concentration gradient drops over 0.7 centimeters. So the concentration gradient is high, just like the hydraulic gradient was high. In the case of advective flux, what happened? Your hydraulic gradient was high, but it was offset by a order of difference in permeability of 10 to the power of 2. That means one was 10 to the power of minus 7, the other was 10 to the, so 100. Here what happens? The order of difference between the two is not 100 but 3, whereas this is almost 120 times. So that is why the diffusive mass flux is larger, 51 times. Let's quickly go back to our advective mass flux and see what did we calculate there. So advective mass flux was 2.6 into 10 to the power of minus 8 and 8 into 10 to the power of minus 8. 2 into 10 to the power of minus 8 and 102. Two things I want to make statement here. One, the advective mass flux and the diffusive mass flux in compacted clay liner are similar, right? 2.6 into 10 to the power minus 8 and 2 into 10 to the power minus 8. But the diffusive mass flux in GCl is much more than the advective mass flux. So GCLs, when the permeability becomes very low, the diffusion will predominate. When the permeability is high, advection will predominate. So the cutoff is about 10 to the power of minus 7. At 10 to the power of minus 7 centimeter per second, permeability and diffusion coefficients in the order of 10 to the power of minus 10 meters square per second, advection and diffusion have about the same role to play. But if you go to 10 to the power of minus 9 centimeter per second for permeability, then you find that the diffusive flux is much more. So in comparison, once again, the GCl is passing more through diffusion. Agreed? Okay. Finally, we look at, we talked about advective breakthrough time, and we are now going to talk about diffusive breakthrough time. So advective breakthrough time was 10 years, 10, 11 years in compacted clay liners and a few months in GCLs. To find out diffusive breakthrough time is a little tricky in the diffusion, because you now have to use transient formulae. You have to use transient formulae. Okay? So here what you will find is that we are going to use Fick's second law. The first law was for steady state condition, delta C by L is a constant. So that is simple to do. So the Fick's second law takes this form. For time dependent unsteady transport of non-reactive solutes in soil by diffusion, Fick's second law says del C by del T is d dash del 2 C by del Z square. Luckily there is a solution for this equation and the solution is the concentration at any depth and at any time is related to the original concentration at the top by this complementary error function Z4 d dash T 0.5. Now you will have to take this formula as a given. We are not going to do this derivation, but what is it that this formula gives me? Okay? You can all read up about this. It's not very complicated, but what does it give me? It tells me that as the solute or the contaminant travels, the concentration is changing. So it's an unsteady case, right? So if you go into the soil at any depth, at any time, so I have, let me say I have a 90 centimeter thick clay. I want to find out at 45 centimeters middle, what is the concentration. If I say the time at 0 time, after 1 year, after 2 years, then Z is 45 centimeters, T is the time, I can put Z here, D dash is given to me, time is known, I can compute this value, right? Once you compute this value, you can find Cz as a function of C naught. Now what is this error function complementary? Standard tables are available, don't worry. If you know beta, you can find ERFC. Okay? You'll have to go back and look up your maths a little bit, but if you find this is beta, if you find this value, then you can find this error function, and quite clearly C cannot be greater than C naught. Can it be greater than C naught? So it can not be greater than C naught, so you will get these values varying from 0 to 1 all the time, 1 to 0. So in this case, we are going to give you a problem, simple problem. How do I calculate breakthrough time? Breakthrough time is when the first contaminant comes through, right? For the purpose of this problem, we are going to say when does the concentration at the bottom of the liner become 10% of the concentration at the top? You have to give some value. You say, no, when the first comes through, it can be 0.00001%. That's a difficult one to do mathematically. So it says, for the previous example, compute the time taken for the exit concentration to become 10% of the concentration at the top of the liner for the time dependent diffusion. So you recall CZT is equal to C naught error function into this. So we are saying CZT over C naught should be equal to 0.1. That means error function of something should be equal to 0.1. And if you go back to this table, error function of something, complementary error function of something should be equal to 0.1, it will come here somewhere, right? And that value is 1.17. So now I know 1.1, I know Z, all I have to do is find out the time t. Okay. So please put Z over 4 d dash t 0.5 equal to 1.7 and please compute the t for me in days, months or years. Do remember that all processes are coupled. Actually, in the field, advection and diffusion are occurring together. So what we are doing here is very, very simplified, but it still does give us an idea of what is happening fast, what is happening slow, how much time does it take. So if this is value is 1.17, this becomes 0.1, which is 10%. So please compute the T for the Z. Please understand that the Z for the compacted clay liner will be the 90 centimeters, and for GCL it will be 0.7 centimeters. You'll have to match out your units, but the values which I've got are 7.75 years and 12.4 hours. But I would like you to compute it on your own and tell me what values do you get. Anybody has some values? In seconds, in minutes, in hours, in weeks, in months, in years. For compacted clay liner? Okay. And what is it for? Do the same for the GCL.
12.42 hours.
So let's see what I got. So I have got about 7.75 years and I have got 12.4 hours. So once again, breakthrough in GCL is faster than breakthrough in CCL. Remember, advective mass flux breakthrough time was 10.7 years. Diffusive mass flux, the time is 7.8 years. So everything is going to happen about after 7.5 years. Diffusion and advection are going to happen after 7.5 years. But in GCL, advective breakthrough time was advective breakthrough time was 3 to 4 months, 110 days. Diffusive breakthrough time is 12 months. So the flux is going to be much, much earlier. It will be lower. Once the breakthrough takes place through the compacted clay liner, the quantum of advective mass flux is going to be larger, but the quantum of diffusive mass flux is going to be smaller. So with this, we get a good feeling. Let's just go back to these examples and the first thing we wanted to know was comparison of the advective mass flux, and what we found was that compacted clay liners had more, about 3 times that of the GCL. But if you look at the breakthrough time, there was a huge difference. This was 10 years and this was 0.3 years. So there was a factor of safety of about 30, which was different. Then when we said what about the diffusive mass flux, and suddenly there the advective mass flux was 3 times for the compacted clay liner. Here GCL has 51 times the advective mass flux. The diffusive mass flux is 51 times. And lastly, the breakthrough times. Again, in years for compacted clay liners, but in hours for GCLs. So with this, we end our discussion today on the solved examples. Given you 2 or 3 facets, one is this action leakage rate. Why do we talk about 1,000 liters per hectare per day? And also, what happens by the composite effect. What happens by the composite effect? And secondly, the equivalence between compacted clay liners and GCLs. So we'll stop here today, and if you have any questions, I'd be happy to answer. Still, I'm saying both advective and diffusive have been treated separately here, very, very simplified. Actually, it will be much more different. The compacted clay liner will not be saturated. So the saturated permeability will not operate till the wetting front moves through it. We have used a saturated permeability, steady state condition. Same thing will happen through diffusion. So we have simplified the problem so that we get at least an idea of what is happening as the leachate passes through the barrier layer at the bottom. Okay? I hope you have a better idea than what you had earlier. I mean, definitely the moment you bring in breakthrough time, the whole thinking changes, and the moment you look at diffusion also, which is so much more important when permeabilities fall. That's important for us for the purpose of design. Okay? Have a good day.